Hello, hello, hello. How are you today? Okay, I'll stop. Something about a microphone makes me want to sing. I'm going to spare you all and just tell you about electrochemistry. So we're going to be doing electrochem for a couple of days. Actually, this will be our longest mini lesson. It actually is a pretty major topic, and when we get to review, we're going to make sure that we come back and I'll tell you some other parts of this that I'd like you to study sort of independently for those of you that are doing well with your reviewing. But this part we're all going to do, and this part I'm going to hold everyone accountable for. And the stuff we do next week, everyone will be held accountable for. So first of all, we need to talk about this idea of oxidation numbers before you can understand what redox chemistry is. An oxidation number is like a charge, but notice in your notes it says that it's a hypothetical charge. The reason why we call it a hypothetical charge is because every element has an oxidation number, even if that element is in a compound that is covalent. So it doesn't have ions, but it's covalent. It has this hypothetical charge that goes along with it. And it's really important to know the oxidation number for an element. And the oxidation number for different elements or elements changes depending on what compound it's in. So you have to actually go through and determine the oxidation number every single time. Even if it's oxygen, it will be different in different compounds. So to know how to do that, there's a couple of rules. First of all, rules 3 through 6. Okay, these rules, you have to learn the order. Okay, it's actually 3 through 7. You have to learn that order. Okay, and I'll show you what I'm talking about. But rule number 1 really is the governing rule, that when you have an element in a compound, whatever the overall charge is on that whole compound is going to dictate what all of your oxidation numbers need to add up to be. So if you have a neutral compound like carbon dioxide, it's got to add up to be 0. The oxidation numbers of carbon and the 2 oxygens have to add up to be 0. If you are doing the oxidation numbers of, say, an ion like NO3 minus 1, then they have to add up to be a minus 1. Okay, so it's got to add up to be that total charge. And if you have a neutral atom, like just copper by itself, or just zinc by itself, or just Cl2 by itself, or just O2 by itself, any pure element, diatomic or not, then it's going to have an oxidation number of 0, which is what its charge is. So you should be kind of familiar with that already. Now, the order. From then on, you're going to be looking for certain things. You're always going to start by looking at the elements in your compound for alkali metal, alkaline earth metal, or aluminum. If you have any of them, then their charge, based on the periodic table, is what their oxidation number is. Then you look for hydrogen. If it's there, it will have its plus 1. And then you look for oxygen. If it's there, it'll have its minus 2. Then fluorine, and then the other halogens. But the key is this last one. You have to mathematically determine the last element in your compound. Okay, so your rules are going to dictate all the way up to the last one, and then the last one has to actually physically be calculated. You may remember this from last year because we did do this last year. So let's go through some examples just so I can remind you how to do this. I have a little system that I like to use for doing this, and at some point you might be able to just do it in your head, which is totally fine. But let me show you how I do it. So for A here, first of all, identify what the overall charge is going to be. This is a neutral compound. See how there's no charge up here? So I know that all of my oxidation numbers are going to add up to be 0. Okay, I can tell that right off the bat. Next, I'm going to look for my order. I'm going to look for what I call the triple A's, the alkali metal, alkaline earth metal, or aluminum. I don't have any of those, so therefore I move on to the next one on your list, which is hydrogen. Don't have hydrogen. Then I move on to oxygen. I do have oxygen. So oxygen is going to have an oxidation number of a minus 2. Now, I apologize for the horrible writing on this. I'm on my laptop, not on my smartboard, and so it's just not going to look as nice. It's going to drive me more crazy than you probably, but I apologize. But I always write the oxidation number above it, and then I circle it. The reason I circle it, oh my gosh, that's terrible. Okay, I'm going to go get past it. The reason I circle it is because I don't want my brain to think that it's a charge, because it's not. It's a hypothetical charge called an oxidation number. Okay, so it's very similar, and so you want to make sure you've got that distinction. Now, I don't care if phosphorus is on my list of given ones or not, because phosphorus is the last one I need to find now. So therefore, I don't care if it's on that list. I have to actually physically calculate it. So I'm going to start with the one I know. I know oxygen is -2. I also know I have 5 oxygens. So 5 times -2 is -10. So the total negative charge coming from my oxygen is a -10. Then I always, this again is my silly system, but I always draw a box. And now I'm going to ignore the compound itself, and I'm just going to look right here and say, all right, something -10 equals 0. So that something has to be a +10. Because mathematically speaking, that's the only thing it could possibly be. Now, that's not my oxidation number of phosphorus necessarily, but it's definitely representing it. If you look, I have 2 phosphoruses. Those 2 phosphoruses must have a +10 total as their oxidation number. So if 2 of them have a +10, then 1 of them has a +5. So these numbers I write up above here are for one single element of that. So my answer to this problem would be what I have right here. That phosphorus would have a +5, and that oxygen has a -2. And you can double check your work, multiply it out again. +5 times 2 is 10. -2 times 5 is -10. Those add up to be 0. And that's the process you're going to do for all of them. So let's take a look at the next one. This one has to add up to be 0 because there's no charge up here. See how this one has a charge right here? That one's going to have to add up to -2. But start with this one. So it has to add up to be 0. I look for my alkali metal, alkaline earth metal, or aluminum first. So I have an alkali metal. So this sodium I know is going to have a +1 for its oxidation number. Then I go on to hydrogen. Now hydrogen's on my list, but remember the very last one you always have to mathematically determine. So sodium is going to be a +1. I don't know what hydrogen's going to be, even though the paper tries to tell me what it's going to be. So +1 plus something equals a 0. So this has to be a -1. So that means hydrogen's oxidation number in this compound is a -1. Now your paper tells you that hydrogen usually is going to be a +1, as we've learned in class many a time. But this obviously is a special situation. I mean, it has to be something else. And in this one, you could have predicted that too, because this was an ionic compound. You could have predicted what those were. But on ones like this that are covalent, or this one we're about to do, there would be no other way to go about doing that. All right, let's move to the next one. So the next one has to add up to be a -2 because of that charge. I look for alkali metal, alkaline earth metal, or aluminum, which I don't have. I look for hydrogen, don't have it. Look for oxygen, which I do have. So oxygen is going to be a -2 oxidation number. So a -2 times 7 is -14 for a negative coming off of that oxygen. So over here, inside that box, something has to add to -14 to give me -2. So that would have to be a +12. And it's 2 chromiums who are sharing that +12. So therefore each chromium would be a +6. So chromium would be a +6. For D, we have a total overall charge of 0, because there's no charge in the upper corner here. I look for alkali metal, alkaline earth metal, or aluminum, which I do have an alkali metal. Now this one has 3 elements, so I'm actually going to use the list to determine the second one, which oxygen, there's no hydrogen, so the next thing would be oxygen. So I know my oxygen and I know my sodium. Sorry about that. So I'm going to have to determine sulfur. So sodium, there's 2 of them. That would be a +2. Sulfur, I don't know. And then oxygen, there's 3 at -2, so that would be a -6. So +2 and -6 gives me a +4 for sulfur, like that. Okay, so sulfur should be a +4. Oh my gosh. I hope your paper looks better than mine. Okay, so that's how you do oxidation numbers. And you're going to have to do that for certain types of problems. I'm going to show you one kind of problem that we'll end up doing it a lot for, but you have to learn that order. So please immediately make that a priority. Again, I call them the triple A's: alkali metal, alkaline earth metal, aluminum, then hydrogen, then oxygen, then fluorine, and then all the other halogens. With that, remember that the last one, even if it's on your list, the very last one you find out has to be mathematically determined. Okay. All right. The first application we'll have for this is this concept of oxidation reduction reactions. A lot of the reactions we've already studied fall into this category. All single replacement reactions fall into this category. But anytime you have a change in oxidation number, you're going to have what's called a redox reaction. And something in the reaction is going to be gaining electrons, and something in the reaction is going to be losing electrons. And we're going to use the oxidation numbers to determine them. So let's just go through this really simple equation and get the oxidation numbers. We're actually not going to even have to do as much work as we were just doing. For example, if you look at zinc, zinc is all by itself. It's neutral zinc. If it's neutral zinc, then it will be zero charge, okay, or zero oxidation number. Now, see this coefficient of a 2? It makes no difference at all to oxidation numbers. The oxidation number is an oxidation number that belongs to that element in whatever compound it's in. It doesn't matter how the compound is reacting with another compound. So all we care about is the fact that this hydrogen has a +1 charge on it. If they're telling you the charge on it, then you're done. You don't even have to do any work. So hydrogen's +1 over there. On this side, again, they're telling you zinc is a +2. They're sort of handing you that information. So a +2. And then it goes to neutral hydrogen. Remember, our diatomics are considered neutral as well. So what we have happening here is two different things. Zinc is going from a 0 to a +2 charge, oxidation number. Hydrogen's going from a 1 to a 0. So 0 to a +2 means that zinc has lost electrons. Remember, electrons are negatively charged. So the fact that it has increased, become more positive, that means it lost electrons. Hydrogen goes from a +1 to a 0, which means it's gained electrons. So hard to write this way. Okay, that is oxidation and reduction. Losing electrons, as you can see right here, is called oxidation. Gaining electrons is called reduction. And oxidation and reduction have to happen hand in hand. If one thing loses electrons, something else is going to gain them. And so this is always going to happen in the same reactions together. There's some little mnemonic devices there to help you with it. Leo the lion goes grr. Leo stands for loses electrons oxidation. GR stands for gains electrons reduction. Or oil rig is oxidation is loses. Rig means reduction is gains. Whatever way works best for you. Also, there's some other terminology which is really, really silly if you ask me my opinion. But somebody decided they should come up with a term called reducing agent. Reducing agent means if something's a reducing agent, that means it's allowing something else to be reduced. If it's allowing something else to gain electrons, then that means it must have lost electrons. So the reducing agent is the same thing as the substance being oxidized, and the oxidizing agent is the same thing as the substance being reduced. You know the AP test loves this idea because they'll write, what is the reducing agent? People will read reducing and think reduction, meaning gaining of electrons, and then all of a sudden they're picking the wrong answer. So make sure you understand whatever agent's on there, it's actually the opposite. Also, you might be thinking, why is reduction gaining of electrons? Because the word reduction usually means to go down. And the reason is because you're gaining electrons, and electrons have a negative charge. So the charge is going down, and that's why it's called reduction. It's a reduction in charge, which must mean a gaining of electrons. So if you look at this last problem, this one, sorry about this down here. This one is a little bit more common, I would say. There's a lot more oxidation numbers to do. If you pause the video right now, go ahead and put all the oxidation numbers on each one of these, and I'll put them on and talk through them as I'm putting them on as well, so you can come back. So pause it, do it, and then come back. Hi, welcome back. For those of you that didn't pause it, you got to see my weird transition. So cadmium is going to be 0 because it's pure element. Look through all of them and see, okay, that's the only pure element we have. Then we go to this one. The first rule that applies is oxygen at a -2. So 2 of them are going to be a -4. Has to add up to be 0. So this one is going to be a +4. H2O, we have hydrogen's rules first, so as a +1, but it still ends up giving oxygen a -2 in order for them to equal 0. Really bad. CdOH2, so the first rule that'll be used is hydrogen will be a +1. Then you'll have that oxygen will be a -2. Then you'll do your math and total 0 to find that cadmium is a +2. Okay, and then it's actually going to be the exact same set of rules here for nickel, because it's the exact same kind of compound. So this will be a +2, this will be a -2, and this will be a +1. Alright, so the reason we did that was to now see what's being oxidized and what's being reduced. So cadmium goes from a 0 to a +2. Okay, so it's becoming more positive, which means it lost electrons. So it is being oxidized. Nickel goes from a +4 to a +2, becoming less positive. So it must have gained electrons. So it is the one being reduced. And you might notice that everything else stays the same. Oxygen was a -2 and a -2 and a -2 and a -2. And hydrogen was a +1 and a +1 and a +1. It is possible for the same substance, by the way, to be oxidized and reduced. You'll see some examples of that on the homework. But really, if a question asks you about what's being oxidized and what's being reduced, you have to figure out the oxidation numbers. It's the only way. Now, on the back side, it starts talking about balancing redox reactions. You actually don't really need oxidation numbers for balancing redox reactions, but we will get into the balancing of redox reactions when we get back. Okay, for this, I want you to really study how to go through and figure out your oxidation numbers, and then I want you to be able to do problems like this. And there's a number of problems on the homework for you to try. And then please make sure you watch that video going over the homework problems. And anything you're not sure about, please leave some details for me in your email, because Monday I will address whatever it is we need to address before moving on. And if you don't ask in the email, then I'm going to move on. Okay, and that's going to be a problem if you don't get it. All right. Alrighty, have some fun.